Solve the inequality. All right, so let's look at example A. We have x minus 3 times x plus 2 squared is greater than 0. First thing we want to do normally is to set the polynomial equal to 0, which is basically going to be, in this case, simply replacing the inequality temporarily with an equal sign, right? Other times we might have to bring things over across the symbol to set it equal to 0. In this case, everything's already on the left, so we're good to go with that. Now from here, we basically have to solve this. In other words, we have to find the x-intercepts, or in other words, the real zeros or the solutions for the polynomial equation that we've created. All right, from there, this one's factored, so it's nice and easy. If we have a product and it's equal to 0, it must mean that either x minus 3 is equal to 0, or x plus 2 squared is equal to 0. Now, of course, that means that x would be equal to 3 in this example, and this could be separated out to x plus 2 times x plus 2 is equal to 0. Then you can solve these separately, equal to 0 to finish it up. And when you're done, you get that x is equal to negative 2 for both of them. Okay, so we have 3 zeros for the polynomial function or polynomial equation we just created. From here, what we want to do then is to go ahead and put these on a number line and test them. Now, the one solution is repeated, so we really can't put that on the number line more than once. So we'll just have negative 2 on a number line and then 3. Now, I put them in the order that they would go from left to right. So negative 2 is on the left of 3 on the number line, and that's how it goes. All right, so in order to finish this first inequality, I have to think about the regions that are formed by these numbers on the number line, right? So in other words, there's an area here that's to the left of negative 2. There's an area here that's between negative 2 and 3. And then there's the area here that's greater than positive 3. So essentially we have 3 distinct regions that we need to test. So I'm going to put down here that I'm going to test some number that's to the left of negative 2. I like nice round numbers. Let's try, for example, negative 5, right? That number is to the left of negative 2. How about if we test a number between negative 2 and 3? I like 0 whenever I can use it because it's nice and easy, so we're going to test 0. And then anything after 3, let's go ahead and test positive 5, right? You could also use 10, you could use 4, whatever you like, right? Whatever number makes it easiest for you to run the arithmetic. Now, what I mean by run the arithmetic is we actually have to plug these numbers into the polynomial inequality and to see if they make it true or false, right? So, for example, looking at the inequality we had originally, if I put negative 5 in, I will end up with negative 5 minus 3 times negative 5 plus 2. And the question, of course, and the question, of course, will be, is that indeed greater than 0? Well, this is negative 8, right, times negative 3 squared. Well, we'd square before we do the multiplication, so we'd end up with negative 8 times 9. That's negative 72, and that is not greater than 0, right? That isn't true. So we're going to say that this is false, right? False. You can just cross it out or put an F, whatever you want. In other words, those aren't solutions there. That part of the number line doesn't contain solutions to this inequality. Okay, so let's go ahead and move on then to the next one. Let's test 0. 0 is nice and easy to test, so we can plug it in. We're going to end up with negative 3, basically, right? Times positive 2 squared, right? Because the x disappears when we plug the 0 in. Is that indeed greater than 0? Well, let's see. It'll be negative 3, right? Times 4. And that's negative 12, and that's not greater than 0 either, right? So we're going to give another false here, saying that that's not a solution either. All right, now what if we use 5, testing 5, positive 5? Well, in there we'll have 5 minus 3 times 5 plus 2 quantity squared. Is that greater than 0? Well, here I think it is, right? Because 5 minus 3 is 2, and that's a positive number. And then we'll have 7 squared, right? So 49 times 2. We don't care about the actual answer. We just can say what? That is indeed positive, so it is greater than 0. So this one is true, right? In other words, this is where our solutions come from. So what I'm going to do is just say, hey, our solutions are all of this part of the number line. Now, do we want to include 3 or not? Well, remember, when you plug 3 in, you get 0 because x minus 3 is 0, and that becomes 0. Now, this is strictly greater than 0, so I don't want to include 3. I'm going to use a rounded parenthesis here instead of a squared off bracket, right? A rounded parenthesis saying that we're basically using all the numbers from 3 up, not including 3, right? And then we're going to go all the way up to infinity. So our final answer then for the problem is from 3 to positive infinity. And that's it for example A. Let's work out example B using the same approach. All right, for example B, we do have things on both sides of the inequality, so we want to move the things from the right over to the left-hand side to set it up to say x cubed minus 9x squared is greater than 0. So I just brought this guy over to the other side. Remember, when it comes across that inequality symbol, it becomes negative. Then we can rewrite that, of course, as an equality. So we'll have x cubed minus 9x squared equals to 0. From here, we need to basically factor and try to solve for the real zeros. So I'm going to factor out the x squared, for example, that's common to both. If I do that, then I'll be left with x minus 9 is equal to 0. Now look, we have a product, and the product is equal to 0, so we can basically say that we can separate them and separately set them equal to 0. Okay, so I'll have x squared is equal to 0, and then x minus 9 is equal to 0. And that, of course, gives you the solution that x is equal to 0, or that x is equal to positive 9. From here, we're going to plot these on a number line. All right, so plotting them on a number line, we'll put 0 first, and then 9 after that to the right. And we'll test the regions that exist here, here, and here. So let's pick a number that's to the left of 0. For example, you can try negative 1 if you like. From 0 to 9, we could try the number 1. That's nice and easy. And then after 9, we can try the number 10. It's a nice round number, right? So I'm going to say test negative 1, test positive 1, and test 10. All right, let's try to plug in negative 1 and see what we get. Negative 1 to the third power, is that greater than 9 times negative 1 squared? Well, negative 1 to the third power is just negative 1. Is that greater than 9 times 1? No, right? That's false. So we're going to say here false, or that is not part of the answer, right? So that doesn't work. Let's try positive 1. All right, so for positive 1, we have 1 cubed. Is that greater than 9 times 1 squared? Well, 1 cubed is 1. Is that greater than 9 times 1? No, that's false as well. So we're going to call that area false as well. And then finally, the last one here, we're going to test 10. So we'll have 10 cubed. Is that greater than 9 times 10 squared? Well, let's see. 10 cubed is just 1,000, right? Greater than 9 times 100, or in other words, 900. So is 1,000 greater than 900? It is, so that means that these answers are true. So our solution is this part of the number line. That goes all the way up to positive infinity. And we don't want to include 9, because when we plug 9 in, we get 0. And of course, this is supposed to be strictly greater than 0. So we're going to just say our answer is from 9 to positive infinity, and keep a round parenthesis on both terms. And we're done.